Hey, it's time for us to get started. I know we love it.
Oh, I didn't even use it. The socks.
For this example, yes.
Socks lost.
Yeah, I think I lost quite a few people rushing through the end of this, so I'm gonna take this. I'm gonna take this more slowly and we're gonna go over it.
Beautiful, I'm here for it.
All right, sounds good. Other announcements, we have a couple of assignments due tonight, so I expect to see a good few of you in office hours. If you don't have it fully ready to go, that's totally okay, but come see me in office hours to get it to that point. We have a review session that we're going to be doing tomorrow, so today is the last day of new content. Review session tomorrow, exam on Friday. Thrilling, truly thrilling time to be alive.
Did you post the exam study guide?
Should be up. Modules inside of the study guides module. Has anyone else seen it?
Oh, I found it.
Okay, good.
We're good.
All right,
It was just-
phew.
My eyes.
If it
were
were
on.
2 days before the exam and I hadn't put up a study guide and people hadn't told me, we'd have a serious problem in this class.
My eyes just falling.
If that's ever the case, please just reach out to me.
Maybe like tell us if it's in the modules, cause I didn't know until like Sunday night.
Yeah,
So
gotcha.
maybe
I
like,
thought that was typical of other people, but I guess it's not.
I didn't know.
well, usually people like kind of let you know, like if teachers will like say, hey, here's the study guide on in modules or something, but things like, I guess just knowing, like having us like get in and cause then you'll know and then people will be able to.
Yeah, I can post more announcements, that is true. All right, let's go over this problem. So infix to postfix conversion was the last thing that we did last time, and we want to make sure this makes sense. So I had you consider this. Then we looked at an actual algorithm that would do it, and then we looked at an example that applied that algorithm to a particular infix expression. So here was the example infix expression. So we wanted to find the associated postfix for A divided by the quantity B plus C minus D. So the way we're gonna do that is we're just gonna follow everything in the algorithm. So the first thing we do, we're just gonna read each symbol. While there are more symbols to be read, well, there are more symbols to be read. So we start with this A. So we go down to these cases, we're gonna look at them in order. You can think of this as just a long list of if, else if, else if, else if, and the very bottom is the else for the cases here. So we want to figure out, is it an operand? Yes, A is an operand. In this case, it is a numerical value, whatever A happens to be. So since it's an operand, we immediately want to output it. So operators are the mathematical symbols like divide, plus. We can technically consider parentheses to be, they're not operators because they don't do math, but they are symbols that are not operands and not operators. So these are our operands. We see the A, there's nothing on the stack. We immediately output the A. We don't even touch the stack. So we figured out which case it's going to be. So we end the case, loop back around the while. Are there more symbols to be read? Yes, there are. We come in, we look at the next symbol. The next symbol is a divides. We're gonna go into the case. It's not an operand, it's an operator. It's not a left parentheses, it's not a right parentheses. It is an operator. So we're going to go into this logic, pop higher or equal precedence operators from the stack. Since the stack is empty, there's nothing for us to pop there. So we're going to finish that and then push the new operator onto the stack. So we're gonna push the divides onto the stack. After we pop nothing off the stack, our output still looks exactly the same. We finish the case, we'll loop around. Are there more symbols to read? Yes, so we're gonna read the next one. It's a left parentheses. So we're gonna go into the case. Is it an operand? No, it is not. Is it a left parentheses? Yes, it is. So we're going to immediately just push it on the stack. So this is the stack contents. You can think of this as like there is a slash on the bottom and a left parentheses above that on the stack. That's what that represents. So rather than storing numbers on the stack, we are storing symbols. So again, we've identified where it goes, the output is what it should be. We've finished the case, we loop back around, are there more symbols to read? Yes, there are. We read the next symbol, a B, come into the case, figure out what it is. This is an operand, so we're immediately going to output it. So that's what happens on this step. We read the B, the stack stays exactly the same. We don't modify the stack at all. We're just going to output the B. So we are building the postfix expression as we go. So the output is the postfix. Input symbol comes from the infix. The stack content are all the symbols that we are reading so far, and the output is just the finalized postfix expression as we are building it. So we read the B, finished the case, loop around, more symbols to read. Yes, come into the loop. See a plus? Is it an operand? No. Is it a left parentheses? No. Is it a right parentheses? No. Is it an operator? Yes. So we now need to pop higher or equal precedence operators off the stack. But of course, we stop before we pop a lower precedence operator or a left parentheses. We look at the top element of the stack and we see that it is a left parentheses. So we need to stop before we get there. So we pop nothing off the stack and we push the plus onto the stack. So the current stack contents now contains a plus on top of the left parentheses on top of the divides. So that's what this stack represents, bottom of stack, top of stack. So here's our stack contents. We finish the case, looping around. We read in the next character, which is a C. Since that is an operand, we immediately output it. We don't touch the stack, we just output the C. So far we've built the postfix expression ABC, but we're not done yet. Looping back around, is there another symbol to read? Yes, it's this right parentheses. So we come into the case. Is it an operand? No. Is it a left parentheses? No. Is it a right parentheses? Yes. Now we need to pop off everything until we get to the associated left parentheses. So we don't want to output anything related to parentheses. We're not going to output the right parentheses, but we're going to pop stuff off the stack until we see a left parentheses, which we will pop off, not append to the output stack, and use that to terminate this inner loop of popping off stuff from the stack. So we first see a plus. So we're popping that and appending it. So the plus comes off the stack. The next thing we pop is the left parentheses, which tells us to terminate popping and appending. So we pop it, but do nothing to the output, but it terminates this pop equal or higher precedence operators until we reach that left parentheses. So we've done that. We have ABC plus with divides still on the stack. Looping around, is there another symbol to read? Yes, there is. It's a minus. So we come in, is it an operand? No. Is it a left parentheses? No. Is it a right parentheses? No. Is it an operator? Yes. It's a mathematical operator. It tells us to do something, to subtract something. So we are going to pop higher or equal precedence operators. Divides has a higher precedence than minus. It's a higher order of operation. So we're going to pop it and append it. So this goes away. Now we see an empty stack. So that is one of the conditions that terminates this process of popping and appending. So we are done popping. We just have to push the operator that we just read, that minus, onto the stack. So we're going to do that. And that's what gives us this stack contents at this step. When we read the minus, the stack contents is the minus, and the postfix that we've derived so far is ABC plus divides. Looping around, are there more symbols to read? Just one last one. We are going to have the D, so we read the D, coming into the case, is it an operand? Yes, we immediately append it, we don't touch the stack. Looping around, are there any symbols to read? No, we're done. Loop over, we come down to the very bottom where we pop the remaining operators from the stack and output them. So we take this minus, we pop it, and we append it. Do we buy that this postfix is equivalent to this infix? Do we think that this process would always work? Can we think of any counterexample of a time where it would fail to convert an infix into a postfix?
Is it trouble at all with multiple parentheses?
It should not.
Okay.
Because parentheses can either be adjacent to each other, in which case we find, that's a great question. So we could either find parentheses that look kind of like this with stuff in between them. If we do them next to each other, then this will be paired with this. We're only going to output the symbols between it. This will be paired with this. But what if we have nested parentheses? What if we have some parentheses, some stuff, another parentheses, some stuff, parentheses, stuff, parentheses? So what the stack is going to look like when we do this is we have, I guess we should say everything before the left parentheses. So I'm going to call that BF before first parentheses, BFB, all of those associated symbols. Then we have the left parentheses, then we have between first and second parentheses. Then we have the second open. Then we have stuff that's in the middle. Then we have our first close, and then we have our between, middle, and last, BML. And then we have our last, and then we have anything after last parentheses. Sure, so these can be multiple things. I'm just trying to bring them into where they go in this process in this stack. So when the first time we would be popping something would be here at this first right parentheses, and we would see that we would go until we hit this left parentheses. But this left parentheses defines this sub-expression. So we would be evaluating that sub-expression before we consider or move on to anything else. Once we do that, then we would eventually see this, which would allow us, or I guess we'd see this, which allows us to pop, and this has all been evaluated at this point. So this will now match with that. And we see that everything in between those parentheses is being evaluated in the order you would expect with the parentheses. Yeah.
Does negative numbers fine?
Yep.
Okay.
How would you tell it what, like precedence?
For this,
Yeah.
it's embedded in the higher or equal precedence operators. So you would need to have some function defined that takes in kind of a first and a second and says, return a Boolean, is this higher or equal precedence? Is the second thing higher or equal precedence the first thing, or something like that, that would answer that question?
Is that like comparative?
It would be, it could be, you could custom create a comparator for symbols. Or you could hard code it for particular mathematical symbols. Either one of those would work in an implementation.
Would this, at least the function, I'm not sure if the application has this issue, but for implicit multiplication, when you stack like a up to operators right next to each other and it's implied that they're multiplied, but there's no operators.
Yeah, we would have to define what that means. In that case, you'd have to keep track of the history of these symbols to say, did I ever see two operands in a row? If so, then there's an implicit multiplication between them. So you could either identify that somehow and do it, but no, it would not handle that by default. This would expect that for a particular infix expression, if we were multiplying, there would be a times symbol. That is not to say that it would be impossible, but it is something that you would have to consider and account for. Other questions? Does this help this process make a bit more sense? We feel like we could replicate this process or code up this process if you had access to the pseudocode. Yes, but exponents are a little bit trickier in that they evaluate right to left rather than left to right. So you would have to use recursion when you find an exponent. That is why I have not done that here, and I will not require it on the homework. It's a little bit more challenging, but possible.
So like anytime you have to like FOIL, like if you had A plus B times CD, does that end up working?
It will work. Yeah, if you have something times and then have a set of parentheses inside of that, and like you want to multiply that, that will work.
That's
Yeah, that is embedded in this logic. Any other questions? Clarifications? Feeling better than we were at the end of last class, give it a little bit more time. Okay, let's talk about some other stack applications and then we will dive into talking about queues, because that is the other part of the homework that I will reveal today. The assignment is called, I've named this myself, I'm especially proud of it, Stacks and Queues and Postfix and Why. So what else can you use a stack for? In computer science, you will find them everywhere. If you want to effectively manage memory, we talked about stack frames as well. That's another possible application, but managing memory, you use stacks for that a lot. As we process function calls, that's done on the stack. It's used very frequently in backtracking and searching kinds of problems. So if you need to search for something and you need to keep track of a history of where you've been in case you want to backtrack to where you were to explore a new path. That can be done on a stack that stores a history. Anything that stores history, so browser history navigation is an example of something that is stored in a stack. When you press the back button, how does it know where you were? String reversal, if you want to reverse strings, you can easily use a stack. Any iterative version of recursive functions, if you want to, in general, be able to do what recursion can do implicitly, you will frequently need to attach a stack to something, which is what we saw when we looked at the iterative version of Towers of Hanoi. That defined a stack and used a stack in the iterative version, which is why it was so long. If you want to implement undo and redo functionality in something, undoing is storing a history, but people don't think that redo is a history of your history. When you undo things, you're storing the history of what you had done in case you wanted to ever redo that. So that ends up being an implementation of two stacks. You have an undo stack and a redo stack. And whenever you undo, you take something from the redo stack and put it on the undo stack. And every time you put something on the undo, or you do something on the undo stack, then you put it on the redo stack. And they kind of go back and forth to store that history of what you had done, and when you backtrack, what you had done before you undid it. That's the redo stack. And there are tons of more stack applications, but the more you think about it, the more you realize that underneath the hood, there is a stack governing many, many, many things. It can be used to design fun game mechanics. If you play Magic the Gathering and use a stack to resolve spells, there are applications all over. Last minute questions on stacks before we transition to talking about queues. Okay, we will transition to talk about queues. I know, I have a problem. Okay, queues are also incredibly useful and used all over the place in computer science, so it's very important that we talk about them. So we talked about stacks as being the life of the party, they're like last in, first out structure, meaning that the last element that was added to the stack is the first element that we take out of it. The question that I would have is, can we get that same constant time running guarantee if we wanted a first in, first out structure? So a FIFO object. As an example, you're waiting in line at a grocery store. Is that a LIFO or FIFO operation? Processing people in line at a grocery store. First in, first out. So my fun mental exercise is, imagine a world where grocery store lines were a stack and not a queue. We process whoever got there most recently. So if you get there right before a rush, you might not make it out until it closes. That would make for some very interesting, I've always wanted to see that game show. Be the world's worst game show, but it would be so memeable. Anyway. With your neighbors, think about the differences between a stack implementation and something that works very similarly to a stack, but instead of being a last in, first out structure is a first in, first out structure. What would need to change? And then also think about the underlying structure. Can we still use a list for this? Something like a linked list or an array list. What would need to change in order to get a first in, first out structure from writing a queue around that instead of a stack around that list? So just think about it. Think about what differences there are, and we'll come back together and talk about it.
You solve this. Add data.
Yeah.
That's the first one. Add data, add data, add data. Then you
Have to dive into the name. I just like it. Very efficient. Very efficient for numerical data where you know the maximum.
largest possible.
Like British people call lines. Like a line in the middle. You're the first person to do the thing gets.
So what happens when you get a data point with when you bucketize it? That's outside of the bucket that you define. It's larger than the largest possible value you made a bucket. So you have to, in real time, figure out what are the new buckets. Or you have to plan for everything in this bucket is anything larger than this other value, but as things change, there may be a finding.
Right, is that even?
It really should be called. There is a bucket, so yeah.
Possible.
For me, it's not particularly relevant. You do, but
I don't think you have to. It's constant to get. It's like so we just lie. Oh gosh. Oh, so you have that.
yeah, it's something in the middle when you modify it depending on the value you care about. So you can modify, if you modify 10, you'll grab the last digit. If you modify 100, you'll grab the second to last digit. Mod by 100 divided by 10. That throws away the last digit. Mod by 10 gives you the last two digits, divided by 10 is your division, throws away the last digits, you have access to the second to last digit. So mod by 10 to the value of a digit, then divided by one digit. Yeah. Yep.
So it's just like.
Yeah.
And it's 5 lakhs.
Any thoughts? What have we decided or discussed on Q's implementation?
Instead of adding at the end, you just add at the beginning and then move from it.
Okay, so yeah, with a stack, we were adding to and removing from the tail of the list or the head of the list. Which one made the more sense there? Adding at the tail and removing from the tail is a lot more efficient than adding at the head and removing from the head. With a queue though, what happens when if we're gonna add at one end and remove at the other? That seems like it could possibly be a linear time operation. If we're gonna use something like an array that needs to move over and make room for something, you're gonna add at the head before you remove at the tail. We know removing at the tail is efficient because we did that in a stack, but what about adding at the head? That seems like that's gonna be a linear time operation potentially. How do we work around that?
So in place.
Just use a linked list. Yeah, don't use an array list, use a linked list. It turns out we can make this work with an array, but yeah, the easy solution is just use a linked list. So queue is a new abstract data type. It is distinct from the stack. Even though there are a lot of similarities between the implementation of a queue and the implementation of a stack, they are separate abstract data types, but we do need to add to either the front or the rear and remove from either the front or the rear. And since we will find out that is actually equivalent in terms of an implementation, it doesn't matter which one you implement or how exactly you implement this. So like with a stack, this is going to be a list with some restrictions to it. So we cannot add in the middle. If you say we are going to add at the rear and remove from the front, then we cannot add in the front. If we are going to add in the front and remove from the rear, then we can't add at the rear. It makes sense when thinking of a queue as a line that you get in the back of the line and you're processed once you're at the front of the line. So we are going to consider and use that as an example as the reasoning why we are going to add at the rear and remove from the front. The rear just means the last place in line, and the front means that you are about to be processed. So if that means that your index is your place in line, basically. And that allows that to not be more complicated. Similarly, we can't remove from the middle or the rear. Once you are in line, you are stuck in line until you get to the front of the line. We can't access or even look at any element in the middle of the queue. There's no way for us to know what's there without processing what's in front of it. So as usual, I like to think of this as a grocery store line. When you get in line, you go to the back of the line. When the clerk yells next, the person who's been in the line the longest gets served. So there's a natural fairness built into it. And we've talked about the underlying structure for a queue. Could we do it with an array list or a linked list? And the answer is, for a linked list, just yes, it works. For an array list, we're going to have to do a little bit of mental gymnastics to make sure that it works in constant time. Because as we've seen, removing from the front of an array list is a linear time operation.
So why is it easier for a linked list to be like a queue than a array list?
Because when you remove from a linked list, you remove the first element, we don't have to shift everything over. We just change the head pointer to heads.next, and we're done. The person has been serviced. They're no longer in the list. So the linked list handles that way more efficiently than the array list. But it is still possible to use an array list. So how do we restrict access to the underlying list? Same as before. We just make the list a private field of the queue object. And then we only allow the user to implement the public methods of the queue that interact with the list in the ways that we are defining our constant time operations. That way, the user has no access to the list outside of the queue's defined methods. So let's talk about the actual challenge. So I've already motivated this, but with a stack, the bottom of the stack is in a fixed location. But in a queue, the actual position, where are the front and the rear in the underlying list? If you force the front of the queue to be index 0 all the time, then we need to go through the linear time operation of shifting everyone up in line. You can think of it like when the clerk yells next, they will only be serviced if you're standing exactly where you're supposed to stand if you're at the front of the line. When that person gets serviced, we have to go through a process where everyone moves up, but you can't move up until the person in front of you is moved up. Otherwise, you will collide with the person in front of you. So the person in position number 2 needs to take a step forward, and the person in position number 3 needs to take a step forward. And all of that process needs to happen before the clerk can call next again and service the next person in line, starting that whole process of moving everyone forward again. But how many steps forward are taken depends on the number of people that are in the line. So if we use an array list, this is the challenge. How do we handle this in that case? So every time we take something out of the queue now, instead of every element taking a step forward, we're just going to reposition the pointer that says this is where the front of the line is. So when we remove from this array list for the first time, we are going to now say, instead of the front pointing at index 0, the front will now point at index 1. And that way the person doesn't need to move, but from the clerk's perspective, where they look when they say next shifts. So do we want to move every element up one spot? No. Every operation needs to be constant. Instead, we keep track of which index is currently the front and which is the rear. Of course, this creates another problem that we need to solve. What is the problem? Can you even see what a problem is going to be if we just implement this as stated? Yeah?
Won't the array just keep growing its.
Yeah, we'd have to keep resizing the array or keep doing something to make sure that the front, once we are done considering the front of the queue being position 0, we never reuse position 0 ever again. The line just keeps moving further and further back. You can imagine now that the clerk has to start yelling for anyone in line to be able to hear them. And then eventually needs a megaphone in order for people to be able to hear them. And then eventually you need a cell phone or something of the sort to say, I know you're 60 miles away, but I'm ready to serve you now. Imagine that grocery store line. Imagine the long, you load your groceries and then you walk 60 miles with your groceries to get serviced. That doesn't really make sense. So if we add a bunch of elements, how do we care about resizing the underlying list? Can the list be resized in constant time? Do we know how list resizing works? How expensive is a list resize? That's a linear time operation, which means we can't allow it. So how do we deal with that? If we can't allow the list to resize, the first obvious solution is to use a linked list, which we've already figured out. But, so the front is going to be the tail, the rear is going to be the head, or vice versa, it doesn't really matter. We'll come back to this problem of how we solve this for an array, because I do have content for it, but we're first going to think of the easy way to do this is with a linked list. So naturally, your homework is going to be with an array list. Yes.
Oh,
We're going to code up the linked list version in class, and then I'm going to assign you the more complicated and harder, and also more likely you're going to see on an interview question. How do you handle it with an array? So let's backtrack a second and think about how do we make this work with a linked list? So what do we need to store to make this work? What are our fields? We need to know where the front is, so something like a front pointer. But if it's always part of the list, and we said that we're going to, the front is the tail and the rear is the head, then the front is always wherever the tail is. Or if we do it in reverse, it doesn't really matter which one we do. If the front is the head, then when we EQ, which we'll talk about, then it's all, we already have something in a list that points to it. It's either the head pointer or the tail pointer. So we need the underlying list. That's going to be one of our fields. Size, Q needs to know how many elements are in it. Yep. We also need to know the maximum number of elements that can be in the queue. But this is only if we're implementing it with an array list. For a linked list, we don't care about it. We'll come back to why this is an important thing to store if you're using an underlying array list. We also need to know the associated index of the first element if we're using an array list. So 2 extra fields are necessary if we're doing this with an array, but we just need the list and the size if we're doing this with a linked list. What methods is a queue going to have? Of course, the methods are named differently from a stack for no other reason than to confuse you. So instead of push, we call adding to a queue an enqueue. It looks exactly like push did. It has the same elements that you want to add. And the definition of the enqueue is it adds that element to the rear of the queue. Instead of pop, we have DQ. It does exactly the same thing as the pop. It's gonna return the element. And it's going to be, return to you the element that was at the front of the queue. But of course, peak is named exactly the same as the stack's peak was. Yeah. We return the element without removing it from the queue. We'll have a size method to return the number of elements currently in it, and that allows us to make the size field private. Because it should be read-only. We don't want the user being able to modify the size of the queue that we think that the queue is, so that needs to be private. And of course, we'll want an is empty as well, just to determine very quickly, is the size 0? Go ahead and spend a chunk of the remainder of class, possibly the whole thing, trying to write an underlying linked list queue. My recommendation is to take a look at the stack that we implemented and try to think about what is different, because it will look very similar. So go ahead and give that a try with your neighbors. There are structures that use them, but nothing that is exactly or would belong exactly in that same family. So for instance, it has the name queue in it, even though it doesn't implement a stack or a queue or use a stack or a queue, but a priority queue is the equivalent of a queue with the associated priority. So when you add an element to the queue, it has an associated priority, and then when you dequeue, it removes the element that's been in there the longest that has the highest priority. The underlying structure for that is not a queue, it is a heap.
Sorry, say that again, I totally just associated.
That's fine. So a priority queue is it's like a queue, but when you dequeue, when you enqueue, you give everything a priority. You can think of this as a low, medium, high. You can think of it as a number between 1 and 10. Doesn't really matter what the priority is, but there is some comparable priority element to it. Then when you dequeue, you are dequeuing the element that's been in there the longest that has the highest priority. So you would take in the longest that's been in there, high priority element. But the underlying structure for that is not a queue, it is a heap. Yeah, it does not use a queue. In fact, it is impossible to use a queue object for that, but a heap makes so much more sense. How are we doing? We feeling able to get started? Anyone stuck and could use some direction? Yeah, what's going on?
Just starting there, I mean, I think I know what the methods, just write the methods, but.
Yeah, so if we look at our code for our stack from last time. The single linked list on a stack, if we look at our code from a stack from last time. I would start here and say, okay, instead of push, we want to write NQ. So we're going to be using the same concept of an underlying list, but instead of an array list, now this is going to be a linked list. And you could make this a singly linked list. You can make this any of the implementations that you have written, or you could import Java's built-in linked list. I like using our own tools whenever because we wrote that, being able to use that is pretty cool. So in order to NQ, instead of, where is that NQ happening? It's either at the head or the tail. Which one did we say we're going to be doing? And or which one do you want to implement? Because it's totally equivalent. Yeah, at the tail would be just fine. So does anything change? This is adding at the tail. So if you want the rear of the queue to be the tail, then this exact line does everything that you want. It puts it at the end of the linked list. However, when we want to implement something like a DQ, which would be equivalent to a pop, there are going to be some pretty major changes to this. Because in a stack, we were moved from the same place that we pushed to. And with a queue, we are not. So what changes and how?
Practically, would there ever be a reason to actually utilize the array list as the underlying structure for
Yes,
queue?
faster access.
Right, okay.
If we needed to access anything, be able to do something, but for a queue, probably not, because you don't ever have, you can't access anything in the middle.
Yeah, for a queue.
Yeah,
Okay.
yeah, so if you're implementing a queue, then. Yeah, it'll be a good exercise to consider that once we've
Right.
looked at a linked list based implementation, what changes for an array based implementation. We should make sure we come back to that and talk about, is there a benefit to using one or the other? That's a really good question to consider.
Select shows.
Well, that's what it is. That's not why it can.
No, that's not like one. It's. Whoa, wait. Go out to get it. I do, but get it. It's like. That's. No, we're going back to talk. There's one that had stacks. Oh, you want to use your wait, it's computer one. This might not work. Everything now that I'm gonna make, right? Sarah, you know your loss. Whatever you have in the field, stop. Yeah. That's not like the first one. It should be wrong.
All right, so I very quickly made my singly linked lists head and tail private, and then implemented a get head and get tail. I'm also gonna go into my singly linked node and do exactly the same thing for the data. Turn these to private. Turn this to private. And then I'm going to, and IntelliJ can do this, anything can do this. There's a generate getters and setters that makes it very easy for you to just select, what do you want your getters and setters? So you select, I want get data and get next. And these give you the basic getters for the associated fields. You have to make changes to this if you wanted something other than just the default return everything. If you want to do password protect this, if you wanted to only allow reading for some reason or setting to certain values in between a lower bound and an upper bound, so like set GPA shouldn't be able to be set to be higher than 4.0, for instance. So you could modify any of those that you need, but it's only going to generate the basic ones. When you do this, it will break some of the work that we've done, and that's okay. We just go change any call directly to next, for instance, to just get next. And it's going to do exactly the same thing within the scope of this. Cur.data becomes cur.getData. That is. So I would just continue to go through and do this, but that will allow us to make a queue that accesses these elements outside of this package. And since this queue is going to use this as the underlying structure, but it is distinct from what it does. It's not doing something with the linked list. It doesn't add to the linked list's functionality. It's a separate structure. That is when I would want to change things from protected to private, because we do still need to access these values, but we do not want to override these values. So we don't want to have the public ability to set them. They should be read-only from the perspective of our queue. So we're going to better encapsulate. It's really annoying to do. I'll go through and do this later, but now we actually have the ability to go through and implement our queue. So that's what we're going to do at the start of next class, is actually go through and finish this off. And then we'll talk more about queues, what we can use them for. Look for an assignment later today. You should at least be able to get started with implementing a stack, implementing the postfix evaluation and the infix to postfix conversion aspects of that. But you will also be implementing a circular array based queue. We'll talk about exactly what that is tomorrow. Not tomorrow. We're doing a review tomorrow. There'll be a long time. We'll talk about that on Monday. Tuesday, we don't have class on Monday. That may make me rethink the assignment a bit, because I don't want to go over a circular queue and then have that be due for you the very next day. Get started, but I will be pushing that aspect of the assignment, possibly the entire time back a little bit. We'll see.
It's like having an opportunity to sit on it. It's just feeling very concerned. It's so move that.
But it's probably just a good idea, right? Yeah, so what I'm gonna end up doing is.
All I'm gonna do, so for you. Whoa, you know,
This is supposed to set.
no.
So like this is me right here. This is. And then.
You and another, and then yes.
And then.